Hello, and welcome to the workshop for Electronics and Control Division. I'm Division Manager Louis Lozano for EE400D 2017 spring semester. So we're making this workshop to hopefully make it easier for people to educate themselves in their own time. So it's easier for you to absorb the information as I explain it. You don't have to sift through all of the information that I post on the website. And although I'll be going over the topics pretty quickly, hopefully you'll jot down any questions that you have. And if you need me to slow down, you can use the YouTube playback option to slow down the video. But I hope to go over this pretty quickly as to not waste anybody's time who's already versed in these things. So in this workshop, we hope to be able to help you out in your component selection. We're going to be talking about motors, stepper motors, servos, sensors, motor drivers, your options for batteries and what you're looking for, power converters, and a few other things. So we're just going to, so hopefully this will help you to understand why previous semesters used the components they did and help you to understand what you can use or why you would change it. So first we're going to start with DC motors. Motors in general. A motor is an electromechanical device that turns electric energy into mechanical energy. And although there's DC and AC motors, for this class we'll be using DC. The cool thing about DC is that they typically have two wires and they're bipolar in direction, so depending on which one you give power and which one you ground, depends on the direction that the motor spins. So something to consider here is we have the equation for torque and power. Here we have the rotational speed of the motor and the power of the motor to get the torque. And torque will play into a large consideration in our prosthetic arm project and hand project, seeing as weight of what the arm can support will be an issue. So here are some things to consider: just the voltage range of the motor, the current, the amount of current the motor draws or needs to operate, the output torque, and the RPMs, which is the rotations per minute. So DC motors are typically higher RPM than surely the stepper motors we'll talk about. These will hit 4,000, 8,000, 10,000 rotations per minute, and they can be controlled using pulse width modulation, or PWM, which is the technique of rapidly pulsing the power on and off. So basically the percentage of time you spend on versus off determines the percentage of RPMs in a proportion to its maximum rating. So if you have the pulse going on and off, on 50%, off 50%, if your motor's rated at 4,000 RPMs, you should be able to get 2,000 RPMs. PWM can be generated out of your Arduino, so we can use that to send the signal. However, it would likely need a motor driver as well. So let's talk about H bridges. So H bridges is a really cool configuration if you're going to be using a DC motor. H bridges, and you can see why it's called an H bridge right here. You've just got an H across the motor. These typically are available as integrated circuits, or you can build yours out of 4 switches. It's literally just 4 switches. And the cool thing is it allows you to reverse the direction of your motor with just some simple programming. It also allows you to break the motor. So if we send current down S1 or switch 1 across the motor and down switch 4, if we close these 2 switches, you'll get the motor spinning in the right direction. If you leave these 2 open and instead close S3 and S2, you'll have the current spinning the motor in the left direction. If you just close the 2 top switches and have the current travel like this, you'll cause the motor to break in place. And if you close the 2 bottom switches, the same thing. If you're going to be using this configuration, you just have to be wary of not closing S1 and S2 at the same time, or S3 and S4 at the same time, which will cause the circuit to short circuit. But other than that, it's a great little configuration, a great tool for us to use. Now we're going to get into the stepper motors. Stepper motors are a really cool tool that we have to use. The stepper motor is a brushless synchronous motor that converts digital pulses into mechanical shaft rotations, and it moves in steps, hence the name stepper motor. So generally a stepper motor is 360 degrees are divided in 200 steps, or 100 or 1.8 degrees per step. Generally you'll send it a pulse, again PWM controlled. You'll send it one pulse and it'll move one step, and we'll talk about that a little bit more. So the types of stepper motors: there's permanent magnet, variable reluctance. We'll be using hybrid. It's what's most commonly available and probably makes the most sense for us to use. Well, let's talk about step modes. So there's a few different modes that that are typically, most motors you can run them full step and half step, just depending on how you program them. So full step typically means you'll get 200 steps per revolution, or that you'll have to send the motor 200 pulses before it makes a complete 360 degree spin. Half step doubles that, and then so 400 steps, so you get a little more accuracy. And micro step is for your extreme precision. It 1.8 degree turn. So what used to be one step is now split into 256 steps. So it's some extreme precision, if you don't want to use gearing to change it, to change your overall rotation. So some advantages of using stepper motors: you have a wide range of rotational speeds. It's proportional to the frequency that you input into it. So if you're sending a pulse very rapidly into the motor, it will spin very rapidly. At the same time, very low speed is possible, just by doing the opposite, sending slow pulses. The stepper motor is quite reliable because it does not use. I turn this way to talk to the screen, but. Because it doesn't have brushes, it doesn't degrade over time. So typically the life of the motor depends on just the bearings inside of it, how long those last. The stepper motor also maintains full torque, as long as it's energized. Even if it's in a standstill position, it'll maintain its full torque. It provides precise precision and repeatability of movement. So because it moves an exact 1.8 degrees every step, if you need it to get to the same spot, you can say move 20 steps and it'll hit the exact same spot every time. So that's a beautiful thing. And yeah, that's my quick synopsis of stepper motors. Any questions, jot them down for this motor or the DC motor, and we'll cover it during the division meeting. Like I said, I'm running through this pretty quickly. So now let's talk about servos. A servo is a DC motor with a servo is a small device that incorporates a two-wire DC motor, a gear train, a potentiometer, an integrated circuit, and an output shaft. Usually 3 wires will stick out of the motor casing. One is for power, one is for ground, and one is for a control input line. Servos are generally rated for 2 things. Generally rated for speed and torque. So normally there's 2 types of servos of the same kind. One that's geared for speed and the other one that's geared for torque. And it also, the cool thing about motors is that it draws power proportional to the mechanical load. So a lightly loaded servo doesn't consume much energy, which is great when we're considering our battery life. We also have, we'll talk about, and this also goes for the stepper motors, but we have inexpensive servos that are made from plastic and more expensive servos made from metals. They have metal gears. So they're a lot more rugged, these metal ones, the more expensive ones. They're a lot more rugged, but they wear faster. And so just things to consider. I've seen on the website that on the internet that they recommend ball bearing servos. If we are going to be lifting heavy loads. And from what I understand, the prosthetic arm and hand will be carrying a pretty heavy load. So our baseball bat, which I consider a heavy load for a little motor to hold up. But servos are also controlled, again, by pulse width modulation. You control its speed and by just varying the electrical pulse width. So here we have, and it's just depending on how big the pulse is, depends on how far the motor will turn. So the servo motor expects to see a pulse every 20 milliseconds, generally, and the length of the pulse will determine how far the motor turns. For example, a 1.5 millisecond pulse will make the motor turn to 90-degree position. Anything shorter than 1.5 will bring it closer to 0, and anything longer than 1.5 will make it closer to 180. So that's what you can see here. You've got the 1.5. This is 1.5 seconds here, 1.5 seconds, and the servo spins directly to 90. Now, why would you use a servo? Servos are meant to rotate to a specific angle, as opposed to stepper motors. So they typically only rotate 180 degrees and aren't meant to free spin as DC motors are, or even our stepper motors when de-energized do. But servos are meant to rotate to a specific angle every time. So when a servo is commanded to move, they will move to the position and hold that position. If an external force pushes against the servo while the servo is holding a position, the servo will resist from moving from that position until its maximum amount of torque is reached, and then it'll break. But in order for it to hold its position, the pulse would have to be continuously sent out to the servo. So that's what the servos are used for. Some of our components, I know the Pathfinder might consider using an ultrasonic sensor. Basically, it works somewhat like radar. It sends out an ultrasonic sound, typically one that we can't hear, and it maps basically the first thing that it hits. Or it tells you how far away the first thing that it hits. It helps for pinpointing things in front of you. Typically only have I believe it's a 30 degree line of sight, and it just bounces off the first thing and records the first thing it hits. So gyroscopes measure angular rotation. We have accelerometers, which measure linear acceleration. Magnometer measures magnetic flux changes. I'm not sure if we're going to be needing that exactly. But it's important to measure certain things as we go along. So batteries store energy, store DC energy, and batteries are rated, especially rechargeable ones, are rated in milliamp hours, and especially the ones we'll use. And there's the little equation to understand what that means. So it's the amount of current for an amount of time gives you the amp hours. Most of them are rated at milliamp hours. If you have questions about any of this, again, you can ask me again. We'll stop here and pick up again, actually. Okay, pause. Okay, and to finish this up, I wanted to talk about continue to talk about the battery. So the battery is a device that stores charge. And here's the equation of the battery and how we can tell the battery capacity. We multiply the current times the amps, or current times the time, the amps times the hours, and we get amp hours. And our batteries will be rated in typically milliamp hours. So we'll see something that says 3,000 milliamp hours or 3 amp hours. And what that means is that that battery can provide, theoretically, 3 amps for 1 hour. I probably wouldn't actually get to that due to heating and other things, but the point is that's what it should do. But it also means that it could give 1 amp for 3 hours. So 3 amps for 1 hour or 1 amp for 3 hours, and everywhere in between. It's proportional. So as we go about selecting our batteries, we should also be aware of that if we connect these batteries in parallel, the capacity that they have adds. So 2 batteries that are 3 amp hour batteries connected in parallel will be 6 amp hours. Provides 6 amps for an hour or 3 amps for 2 hours. If we connect these 3 amp hour batteries in series, we'd still get 3 amp hours out of them, but the voltage that we can use is then increased. So more than likely we'll probably need to use a DC to DC converter and voltage regulators, only because it's very likely that our project will not, the different components of our project will need different voltages. And so with only one power supply, we'll need a way to give the components the voltages that they need. We'll be able to use these devices. Also, these motor drivers, our motors will typically pull a lot of current and a lot of power in general, and will require their own driver, supplying them the voltage and the current that they need. These are typically available and able to connect to our Arduinos. So just be aware of that. These are some stores that you can online shop for these components. There are obviously more, but these are the ones that came recommended. And this is where I got, these are some of the sources that I also have on a separate sheet. So along with this PowerPoint, that will be uploaded, I'm also going to put the, upload the content that I derived the PowerPoint from. So if you really want to read through it all, it'll be up there for you. More importantly, and probably the most important part of this is going to be this lecture series from Professor Hill. In his EE 442, he goes through his own lecture on sensors and actuators and their integration with Arduino and MATLAB. So if you were to look at this, which will also be on our website, I'll link to it, you'll see that he puts examples of the stepper motors and the servos that we talked about. He gives their schematics, their truth tables, how to wire them. We have some schematics how to wire them, the 2 different resistors. But he also provides how to connect them through Arduino, which is immensely helpful. So as you're going through trying to connect your stepper motors, your servos, and he gives not only the commands but also examples on how to use them. I won't go through them explicitly because each project will require different things, but no, this is how it's done. And the steps are pretty easy to go through. And here we have the ultrasonic sensor, which has a radius of 30 degrees. Awesome. So he goes through again how to connect it and just examples of actual MATLAB or Arduino code that you can use for your projects. And I will also be linking to this on the website. So thank you so much for watching, and I hope that you learned something new today. Thank you.